All right, welcome in math class. All right, so in this video, I'm going to introduce how I expect your composition notes to be done. So here you can see I have an illustration. This is supposed to be an illustration of your composition notebook that I got right here. Okay, and on the front you're going to have Math 2020 notes, and you're going to write your name here. So for example, my name is Jake Shaheen, so I'll put Jake Shaheen. All right. Now, once you've got your title page or your cover set up, we're going to open the book. We're going to open your composition to the very first page, and we are going to open up by creating a table of content. All right. So at the top, you write 2020 Math Notes, table of content. That'll be on the very first page. In this top right corner, you'll have the page number, and we'll have a list going down here. You don't need this. We're going to skip 3 pages from this. So from here, I want you to skip 3 pages, and then 8th grade, this will be your first page of notes. So what you're going to do is you're going to come up after you skip your 3 pages. You're going to put a 1 in the top right corner right here, and that's going to let you know that this is your page 1. And then you're going to come back to your table of contents, and everybody's going to have the first page for their first page of their table of contents, and this page is going to contain rules of exponents. So we're going to come back and we're going to write rules of exponents right here. Now, as I mentioned before, no one has the same handwriting, so pages 2 and onward will likely be different. Some of you will be able to some of you will have smaller handwriting. You'll be able to fit more on a page. Some of you have bigger handwriting. You won't be able to fit so much on a page. From here, it will vary a little bit page to page, but everybody's going to start with this first page. So your first page in your table of content, page 1, rules of exponents. Now, let me give you an explanation, breakdown of what's going on with all of these notes right here. All right, 8th grade, you're getting the short end of the stick because you have a lot of pages of notes because there's a lot to talk about in this lesson. And it's very important that you learn these things going forward into Algebra 1, which most of y'all will be going to. So, first page of notes, rule of exponents. So this first part right here is just a diagram of what an exponent is, parts of an exponential expression. The big number is your base, that is the number that you are multiplying, and your exponent up here is the little superscript. It's the little number up at the top right next to the big number, and that tells you how many times we are going to multiply that number by itself. Correct? Okay, good. So what does an exponent tell me to do? Well, the exponent tells us to multiply the base by itself the exponent number of times. For example, we have 4 to the 3rd power, 4 with the little 3 with the little 3 superscript. That's going to tell us to multiply 4 times itself 3 times. So 4 times 4 times 4, which equals 64. So we want to simplify or evaluate that exponential expression. 4 to the 3rd power, 4 times 4 times 4 equals 64. You can grab your calculator and check and make sure, but I promise. So we say the base is raised to the power of the exponent. So again, here we have 4 to the 3rd power, and we say 4 to the 3rd power. Great. Fantastic. Take your time and pause it if you need to get all of this. Otherwise, I am going to move forward. All right. Every number and variable has an exponent. So what about a whole number like 3? Well, that is just 3 to the 1st power. Anything to the 1st power is equal to that number. But I give an illustration of why that is the case, right? But even let's say variables. So this variable x doesn't have a visible exponent, but there is an implied exponent of 1. So x equals x to the 1st power, or x to the 1. Okay, if the number or variable does not show an exponent, it has an implied exponent of 1. Therefore, and I think there's an E at the end, there's misspellings in these, anything raised to the first power equals that number. So a million to the first power is just a million. A gajillion to the first power is just a gajillion. Great. Fantastic. Riley to the first power is Riley. Great. Monomials. Monomials can be a number, a variable, or the product of both. Now, I know that with you guys, I used this term last year, and I know last year was a million years ago, but with monomials, okay? Monomials can be a number, a variable, or product of both. So product, what's happening right there? Well, what does that imply? It implies multiplication. So as long as you're multiplying stuff together, you're good. Okay, you still have a monomial. So here's some examples of a monomial. 3, a number, right? 3 is a number. 3 is a monomial. Or we could have x, a variable. It's a variable. It's just one variable, so it's a monomial. Or we can have the product of both, the product of the number and the variable, 3x. Remember, when you have the number bumped up against the variable like that, that implies multiplication, so that's what's happening there. Okay, a monomial will also be known as a term, so get used to hearing it like that. If I say combine the like terms, that means you're going to combine like monomials, okay? Then those terms will be used interchangeably. Polynomial. So for those of you who may know your Latin, mono means one. Poly means more than one. A polynomial is the sum of multiple monomials. For example, 3 plus x plus 3x. So again, it's the sum of multiple monomials. So what is sum implying? Sum implies what operation? It implies addition. So you have 3 plus x plus 3x. Very good. Please take your time. Make sure you finish taking all of the notes here, and we'll be right back and we'll talk about the rest. All right, so your next page of notes is going to start off with expressions versus equations. Mr. Shaheen, I thought this unit was over exponents. Yes, it is, but there's a few things we need to talk about before we get there, okay? We just need some of this is a reminder from last year, but anyway, we need to talk about this. So expressions are mathematical statements. For example, 3 plus 5 is an expression. Equations are expressions of equality. 3 plus 5 equals 8. So remember, we talked about that last year. What's the difference between an equation and expression? Equations have an equal sign. Expressions don't. That's as simple as that can be, okay? But it's important for you to have those terms. So if I talk about an expression, it means when a mathematical statement like this that doesn't have an equal sign in it, right? Equations, equations have an equal sign, expressions don't. Monomials and polynomials are expressions. Simplifying polynomials, that's where we're going to go to next. So simplifying polynomials, expressions, combining like terms. So take your time, get these notes up here, and then we're going to drop right down here, and we're going to come to simplifying polynomial expressions, combining like terms, and I'm going to try and fit as much as I can into the screen right here. No, this is fine. We'll just stop right here. Wait, how much of this do I want? Okay, this is good enough right here. Great. Okay, so combining like terms. So I mentioned that term is an interchangeable word with monomial, right? So what we're doing here is we're combining like monomials. We're combining like terms. Okay, so what does it mean for something to be a like term? When a polynomial expression features monomials with similar variable terms, we can add their coefficients. So, in this case, we have 2x plus 3x. Well, what is their variable? Both of these monomials have a variable x, just x. So that means that they are like terms. They have common variables behind them. Okay, and coefficient right here, I'm going to give you a definition for that. We've heard that word last year. Coefficient is just a little number in front of the variable, right? It tells you how many times you're multiplying the variable by itself, or whatever by itself, right? So 2x, and you can see I wrote it out over here, equals x plus x plus x plus x plus x, which is 3x, right? 3x is 3 times x, which is just x plus x. Remember, multiplication is just repeated addition. So if we have 2x, that's x plus x, and 3x is x plus x plus x, okay? And we're adding all of that together. So when a polynomial expression features monomials with similar variable terms, we can add their coefficients, which is what we did here, to get us 5x. So we have 2x plus 3x, that equals 5x. And I guess I should maybe try to get that on there. Equals 5x. Can I do that real quick? Can I do that without? Okay. Y'all give me a quick second. Hold up. Anyway, 2x plus 3x equals 5x. Okay. When the polynomial expression features monomials with similar variable terms such as x, we can add their coefficients. Now, what is a coefficient? You may or may not remember the term from last year. You may remember me saying it, but maybe you don't remember what it is. Coefficient is the numerical value that the variable is being multiplied by. It's the little number in front of the variable. So we have an example right here, 3x. Underline the 3 right there. Your 3 is the coefficient. That's the number hanging out right in front of that variable right there. All right, pause the video if you need to. Take your notes. I'll move forward. And it's the last bit on this page. If a variable does not feature a coefficient, which that whole word is on the page? Yes, it is. If the variable does not feature a coefficient, then it has an implied coefficient of 1. So x equals 1x. Remember, multiplying anything times 1 doesn't change its value. So x has a coefficient of 1. Just ask the question, how many x's are there in x? It's just 1x. It's a coefficient of 1. Can we simplify this expression, x plus 2x? No, we cannot, because x does not equal x times x. We couldn't just add those coefficients here because these are not the same base. All right, and we're going to be dealing with that a lot this semester, so we'll probably get more notes on that. But let's go ahead and continue from here. All right, we're going to continue that discussion right now. Next page of notes, simplifying polynomial expressions continued. What if we have an example like this? What if we have 3 plus x plus 3x plus 5 plus x squared? Well, we can use the commutative property to move like terms closer together. The commutative property allows us to move around any numbers that we are adding in an expression, such as 2 plus 3 equals 5. Well, we can just change that to 3 plus 2 equals 5. It's the same thing. So 3 plus 2 equals 2 plus 3. They're the same thing. So the commutative property lets move things around that we're adding together. So use the commutative property, and I'm going to move the 3 and 5 closer together. That's what I did here. So I have 3 plus 5 plus x plus 3x. Those are common terms. So I have my 3 plus 5, which are numerical terms. They're just numbers. We can add the numbers together without any variables. They're like terms. They're numerical terms. Then we have x plus 3x. Those are what we'll call our x terms because their variable is x. And then we have x squared, which again is different than x, as it's not the same variable term, right? X times x does not equal x. They're not similar terms, so the x squared is all by itself. Nothing to match up with it. From here, okay, make sure you take your time. Then we're going to come down. And then we're going to come down. We can just add the numerical terms. Add the coefficients of the x terms and add x squared. So You can see right here, I did it in parentheses. 3 plus 5 plus 1x. Remember, I put a little star above there. There's an implied coefficient of 1 in front of x, just like we talked about. If there isn't a number in front of the variable, it doesn't mean it doesn't have a coefficient. It's an implied coefficient of 1. So we have 1x plus 3x in parentheses, since those are common terms, plus x squared, which is all by itself. We can add 3 plus 5 to get us 8. That's our numerical value, plus 1x plus 3x gets us 4x plus x squared. This is as simplified as this expression can be. There are no more like terms for us to combine. We cannot add any of these terms together because none of their variables are common. So that's as simplified as this polynomial expression can be. Okay, so I know some of y'all were curious about this earlier because, man, we sure went off on a tangent about monomials, didn't we? Well, here we go. We're getting back into rules of exponents, all right? So, rules of exponents. First rule, when multiplying like terms, we can add exponents, and I mean like variable terms. So this is different, right? We couldn't add x squared and x cubed together, so we couldn't have x squared plus x cubed, or x to the second times plus x to the third, but we can multiply them together. X squared times x to the third equals x to the 2 plus 3, or x plus 5. I'll give you another concrete example where we have 4 squared plus 4 to the 5th. Oh, God. Oh, God. I definitely need to change that. Okay, hold on. Okay, you're gonna be in class with Mr. Shaheen live, so he's gonna fix that live in the thing for you, okay? Because we can't add. Oh God, I even lost where I was now. We can't add. I'm right here. We can't add 4 squared plus 5 squared. Okay, that's a multiplication. 4 squared times 4 to the 5th equals 4 to the 2 plus 5. Okay, that's not a plus. Multiplication. We fixed that. We talked about it in class. Okay, equals 4 to the 7th. All right. But what if we have 2x to x squared times 3x cubed? What can we do? We're multiplying here, so we can use the commutative property because we're multiplying to move common terms close together. Now look. There's a dot separating these things, but again, it's one monomial because everything's being multiplied. So since everything's being multiplied, we can put our coefficients or numeral values together. We're going to multiply 2 times 3, and we're going to multiply x squared times x to the third power. Now when we do this, we just multiply the coefficients. We just multiply the numbers together. They're just numbers. So just multiply them like it's a 6, and when we multiply common bases, x squared and x cubed, we add them. 2 plus 3 is 5, so we get 6x to the 5th power. We multiply numeral terms and add exponents for common terms. Great. Take these notes. Please make sure to make that change, Mr. Shaheen. If you haven't already, this is not plus. This should be times. Bobby, go ahead. Rules of exponents continued. Okay, so when we multiply like bases, we can add the coefficients, but when we divide like bases, like terms, we subtract the exponents of the divisor from the exponent of the dividend. So in this example, we have x to the third divided by x over 2, x to the second power. So we're just going to subtract the exponents here. So we'll have x 3 to the 3 minus 2, which is x to the first power, or just x. What if we have something like this? 4x to the 7th divided by 2x to the third. What are we going to do? Then we still subtract the exponents of the common terms. So we have x to the 7th divided by x to the third. So we subtract 7 minus 3. That gets me x to the 4th power. And okay, actually, let me come down here. Make sure you take all the notes. We're going to come down. Then we can put our numerical, the numerical part of each one of these terms together, and we can divide 4 by 2. So just like when we multiplied the numerals together, like the numbers. Here we have the numbers again, and we're just going to divide the numbers. So we can divide 4 by 2, and 4 divided by 2 is 2, so we're left with a numeral of 2, and x to the 4th, because 7 minus 3, so we have 2x to the 4th. Hope that was perfectly confusing. Exponents raised to a power. When raising exponents to, okay. So this is going to be a new rule. Exponents raised to a power. When raising exponents to another power, and we're going to get into this in the lessons if we haven't already, we multiply the exponents on the outside of the term of the parentheses with the exponents on the inside. So we multiply the exponent outside with the exponent on the inside. So for example, we have x to the 3rd squared, so it's x to the 3rd times itself twice, so we're going to multiply x to the 3 times 2, which equals x to the 6th. What if we have a situation like this, where we have x squared y, so that's x squared times y to the 3rd power. Then we distribute the exponent on the outside to all exponents inside. So all of these exponents need to be multiplied by the 3 on the outside here. So we take the 3 and we multiply it times x to the 2nd power, so 2 times 3, y to the 1st power, so it's 1 times 3, we get x to the 6th, y to the 3rd. Again, I have that little star here just to remind you that there's implied one exponent. Fantastic. Okay. Okay, and then we'll deal with this week as well. There's going to be more rules of exponents. I know. Alrighty. Don't worry about it. It's going to be a million of them. All right, this is important though. All right, but the last thing that you're going to have in your notes for this week is that any number or variable raised to the 0 power equals 1. So for example, we have 100 to the 0th power. That equals 1. X, we don't even know what x is. X could be any number in the universe, but x to the 0th power equals 1. We got xy, so again, we don't know what that value is, but it doesn't matter because if it's the 0 power, it equals 1. So anything to the 0th power equals 1. All right. That's all your notes for this week. So sure you get them, talk about them, have questions for me. I'll see you on the next one.